Welcome to Maths for YouTube channel. A past question on complex numbers. Sketch in an Argand diagram the locus of the points that represent complex numbers z satisfying argument of z minus 2 minus 2I equal minus 3 pi by 4. Hence or otherwise, find the minimum value of the modulus I z bar plus 1 such that argument z minus 2 minus 2I equal minus 3 pi by 4. Let's start with the first part. Find the locus of z with that given condition. Z is x plus iy, the standard form. And the condition given is argument of z minus 2 minus 2I equal pi by 4. So the first part is given, is the starting point. First of all, that if it's an argument given in the argument and given, the locus should be a straight line. That's what I just wrote it here. If the condition for the locus is an argument, the locus would be a half line, start from a pivot point. So they start from a point, a line as well. So, right, let's the locus of z is argument of z minus, so I just rewrote it or rewritten it, z minus inside a bracket 2 plus 2I, just to find the pivot point or starting point, equal minus 3 pi over 4. So from that, we can identify the pivot point. The pivot point is 2, 2, plus 2 plus 2. So the real part is 2, the imaginary part is 2. So the Argand diagram, so the real axis and imaginary axis, 0, 0 starting point. So the locus 1 is the line. So the first part is given the pivot point for z. So that is 2, 2. The argument, the angle is given minus 3 pi by 4. So in other words, clockwise 3 pi by 4. So the angle with the parallel to real axis, and it's actually going through 0, 0. But if someone feel that, does it actually go through 0, 0? Because I wrote it, it's the point 2, 2 is on that locus. That's why it's going through 0, 0. But we can prove it. We have a quick look. So if the line, normally line equation, mx plus c. The angle here, pi by 4. So m equal tan pi by 4, that is equal 1. So this equation now, x plus c. So y plus xc. Then again, the point 2, 2 on that the line, therefore, substitute that 2 equal 2 plus c. So c equal 0. Therefore, equation x equal y or y equal x. So that is the equation. The locus is started from 2, 2 downwards and the line. So the line will not go beyond 2. So the limit y less than equal to x is less than equal to. That's the first part, the Argand diagram and the locus drawn. So, right, next part is find the modulus of I z bar plus 1. And again, is find the minimum value of that. We will come to that later. So I z bar plus 1. Instead of 1, I just wrote it. So 1 equal minus I squared. So I squared is minus 1. So 1 equal minus I squared. Instead of 1, I put minus I squared. Again, took I out. If I take I out, z bar minus I, because of I out. Then again, modulus of that is I z bar, I z bar plus 1 is equal modulus of I times z bar minus I. The modulus of I is 1. Therefore, we can ignore that. So what we have, modulus z bar minus I. So then again, I just wrote modulus of z plus I, z bar minus I, z plus I. That the standard, the property of complex numbers, but we can do a little work and explain it. So this z bar minus I, z bar is what the conjugate of this z, so that is x minus iy and minus I. And then that modulus means that I took minus I out, so that modulus of that, x minus I modulus that. But the property of the complex numbers, if this x minus I and its conjugate, it's bar. That's sort of what this one is, sort of, not sort of, the x minus I y plus 1. That is what the conjugate of x plus I y 1. So it's just simply that. But the conjugate and the conjugate, the modulus of conjugate and the actual complex modulus is same. So that is all I did actually. X minus I times y plus 1. That is purely is conjugate of x plus I plus 1. But the modulus are same. So this modulus same. Then again, so it just, if you sort of separate it, x plus iy is z, and then plus I. So x plus y is bar, the bar on the top. So the bar on the top can take it out if it's just the modulus. So the modulus are same. The conjugate and the modulus are same. So this is z plus I. That is exactly what I have written it here. So it's just an explanation of how would I found this z bar minus I, modulus of z bar minus I, just a modulus, and modulus z plus I. Then we could rewrite it just to find the another vector, z minus minus I. So it's the complex, so we can represent as a vector. So z is z minus minus I. It's another as a vector. I just drawn this part of that. This is the modulus, the locus of z, and this is the origin, and again this is z, this one z. So because of along this axis, at this point, just make I put a here. It's a point on any point on that the locus. Again, minus I means this is here 0 minus 1. So this is the vector minus I. So if you look at this diagram, triangle OAB. So it just do a vector. OA is z. OA is z. And then OB is the is one minus I. So BA is from this to that. BA equal OA minus OB is a vector addition or vector triangle addition. Vector triangle used for vector addition, or vector algebra, if you want to call it in generally. So z, this is OA is z. Minus OB is minus I. So for the modulus of that equal, it's the B, the vector of B, because of this z minus minus I as a modulus is equal to the left hand side B as a vector, the modulus of that vector. Modulus of that vector is BA. But that distance, BA or AB distance, if that to be a minimum, then it has to be a perpendicular. So it's a distance from a point to a line. It will be minimum when that line will be a perpendicular. So it's just BA minimum is a perpendicular distance. That is simply use that OAB right angle triangle because of this. The here is it's the 90 degrees perpendicular. So just a simple sign. This one will be pi by 4. So sine pi by 4 is the 1 is the hypotenuse. So BA minimum, the opposite side equal 1 hypotenuse sine pi by 4. Therefore, sine pi by 4 is 1 over root 2. So BA minimum, or in other words, this one. So Z minus I, that's what is we just proved it in the I Z bar. I Z bar plus 1. Z bar plus 1 plus 1 equal 1 over root 2 as minimum. Thank you. Please subscribe the channel and share the contents with other students and friends. Thank you.